The track laying process begins with preparing the track bed by grading, leveling, and compacting the subsurface. Old sleepers are removed using clip-releasing devices, and the old rails are lifted and shifted aside. The ballast is then cleared and leveled. Fresh concrete sleepers are delivered alongside the machine and placed accurately on the prepared bed by gantry cranes. Long rails, preheated to reduce stress, are shifted into position and clipped onto the new sleepers. Excess ballast is transported to a screening unit that separates clean from fouled material. A ballast tamping machine packs fresh ballast under and around the sleepers and rails, ensuring stability. The process is finalized by a ballast regulator that shapes the track profile. Throughout, automated track-laying machines coordinate these tasks efficiently, replacing old tracks with new ones in a continuous operation that improves speed, precision, and safety in railway construction and renewal. The installation process of high-speed railway tracks using the Texas system begins with an essential preparatory phase. First, detailed topographical surveys are performed to establish a precise secondary network. This involves marking out landmarks, rods, and saddle points that serve as reference positions along the route. A dedicated installation platform is then used to collect detailed data and verify the accuracy of the construction line, allowing engineers to make any necessary corrections. Following the topographical setup, the next critical step is the systematic distribution of railway sleepers. These sleepers are carefully positioned along both sides of the platform on the rail tracks. The sleepers must be arranged accurately and spaced properly, as they provide the foundation for the rails and bear the loads of the passing trains. This step lays the groundwork for the rapid installation of the rails and significantly impacts the overall efficiency of the project. Once the sleepers are in place, the installation team extends the bottom track layer along the full length of the prepared section. This base layer serves as the stable surface on which the rails will be mounted, ensuring both stability and precision. At this stage, the system introduces its main innovation. It eliminates the need for an auxiliary track, which is commonly required in traditional methods. Traditionally, an auxiliary track built from second-hand materials such as wooden sleepers and lighter rails is constructed to facilitate the unloading of long welded rail bars carried by track trains. This auxiliary track typically spans 4,000 to 4,500 meters and is necessary because the welded bars, often 270 meters long, need manageable support for unloading. However, building and maintaining the auxiliary track adds significant time and cost due to material scarcity and complexity. Instead, the system uses an unloading track gate that operates directly on the railway sleepers already placed. This allows for immediate unloading and mounting of rails without auxiliary track construction. To enable this, sleepers are positioned at twice the length of the track section to provide enough room for rolling unloading machines to work continuously and maintain safe distances between unloading and mounting. Using this method, the leading track can be unloaded with 8 long welded bars, covering approximately 2,160 meters. Simultaneously, the parallel track can accommodate 12 bars, totaling 3,240 meters. Finally, this system also allows mounting operations to start earlier than usual, shortening the entire construction timeline. The result is a high-quality track installed in significantly less time, proving the Texas system's superiority in high-speed railway construction. New track laying using the S2PV system begins with the assembly of 11.6 kilometers of track panels at the worksite base. 2 panels are loaded at a time onto the transport unit. The entire system, including PEEM and LEM handling machines, is remotely controlled for safe and efficient operation. The loaded panels are transported to the laying point. A connection ramp is first deployed to allow smooth panel transition. The PEM telescopic gantry lifts the first panel into position. After precise slewing and positioning, the ramp is retracted, and the first 18-meter-long panel is accurately laid on the track bed. The process is then repeated for the second panel. This reverse and repeat sequence continues for all 645 panels. The S2 PV system enables fast laying of up to 200 meters of track per hour using 36-meter-long plain track panels. Its compatibility with other systems like PEM, LEEM allows flexible deployment in various rail networks. The integration of diesel-powered lifting equipment, PEM XL, LEM 460, and LMC 4611 ensures high lifting capacity and maneuverability. With remote control operation, the system guarantees both productivity and worker safety during switch and track installation. Thermite welding of railway tracks begins with preheating. The distance between the bottom of the heating nozzle and the rail surface is adjusted to 47 to 53 millimeters. The preheating nozzle is positioned vertically downward at the weld gap's center. After igniting the flame and adjusting it to a core, the device is set on its bracket. The flame should evenly heat both sides of the sand mold, reaching 45 to 55 millimeters in height. Uniform red coloration on the rail ends indicates sufficient preheating, typically lasting 5 to 8 minutes depending on the rail type. After preheating, the gas valves are closed in sequence and a plugging rod is prepared. Next is ignition and pouring. After removing the preheating device, a diverter plug is inserted, and the crucible is placed on the sand mold. A high temperature match is inserted at a 45 degrees angle to ignite the thermite. Within 8 to 15 seconds, molten steel forms and pours into the mold. The reaction calms in 6 to 18 seconds. The crucible is removed after 1 minute and the solidified slag is then cleared. After 6.5 minutes, the sand, mold, and sealing materials are removed. At 8.5 minutes, excess metal is sheared using a rail shear machine. Risers are bent or separated. If temperatures are below 15 degrees Celsius, a heat shield is used. Finally, hot grinding is performed carefully to ensure an arch of 1 to 1.5 millimeters. Once cooled to ambient temperature, cold grinding is done to achieve precise flatness, completing the weld. The turning of railway wheels using the DPL 2600 CNC-controlled gantry lathe is fully automated and optimized to increase efficiency and machine life. First, the wheel is positioned and clamped on the machine bed. Once fixed, the CNC system starts the machining sequence. The lathe automatically detects and adjusts to cutting conditions in real time. When favorable conditions are identified, the machine increases the cutting speed to increase productivity. Conversely, in less than ideal conditions, the machine reduces the speed to protect the components and prolong the operating life. This automatic adjustment eliminates the need for manual intervention during operation. The user-friendly interface allows the operator to follow sequential procedures that guide them step by step through the machining process. All relevant information is centralized and easily accessible, streamlining the workflow and reducing the possibility of errors. During the machining process, digital applications provide real-time updates, such as warning messages and troubleshooting instructions. Additionally, a preventative maintenance planner ensures optimal performance and reduces unplanned downtime. During the process, the wheel profile is restored to its original shape, then the wheel is removed and labeled by the worker. The machine DPL 2600 ensures high accuracy and repeatability, making it ideal for rail maintenance depots looking for consistent quality and operational efficiency in wheel set refurbishment. The manufacturing process starts with semi-finished machining of the forged wheel blanks. Each blank is carefully mounted on a CNC lathe, where rough turning is performed to remove excess material from the front and back faces. The inner bore and hub areas are also roughed out, ensuring that the wheel has the correct initial shape and dimensions. Special care is taken to maintain concentricity and symmetry to ensure proper balance during operation. After rough machining, the wheel undergoes quenching and tempering processes to improve its hardness and mechanical strength. This is done without additional heating during machining. Once heat treatment is complete, the wheels proceed to finish machining, where precise turning of the tread, flange, and hub surfaces is carried out. Excavators load large concrete blocks into recycling lines, where crushers break them into smaller pieces. The material is then sorted by size to separate fine aggregates from larger fragments. Rebar and other contaminants are removed for separate recycling. The cleaned, crushed concrete is reused as aggregate in new concrete, as road base, or for landscaping, reducing the need for natural materials and supporting sustainable construction practices. The production of concrete sleepers begins with the precise positioning of steel reinforcement cages within high-precision steel molds. These cages are pre-assembled by automated welding systems and ensure structural stability. Pre-stressing steel wires are then threaded through the molds and tensioned using hydraulic jacks to a specific force. This pre-stressing process improves the sleeper's load-bearing capacity and resistance to cracking. Once the reinforcement and pre-stressing system are secured, high-performance concrete is mixed in automated batching plants. The mix design includes cement, aggregates, water, and additives to ensure high early strength. The concrete is then poured into the molds via a traveling bucket or casting machine. Simultaneously, internal or external vibrators are activated to ensure compaction, remove entrapped air, and guarantee proper bonding with the steel. Depending on the process, either immediate or delayed demolding is used. In immediate demolding, steam curing is applied within a controlled chamber to accelerate strength gain. Sleepers reach required strength within hours and are demolded using robotic systems. In late demolding, the molds circulate through a curing tunnel where temperature and humidity are carefully regulated for 12 to 24 hours before demolding. After demolding, pre-stressing wires are cut, transferring the tension to the concrete body. Each sleeper undergoes dimensional inspection. ultrasonic testing of wire tension and surface quality checks. Automated marking and tracking systems record production data. Finally, the sleepers are stacked using robotic manipulators. Vollert's fully automated mold circulation systems ensure high throughput, consistent quality, and traceability throughout the production cycle, meeting international standards for railway infrastructure. The production process begins with the preparation of a fixture for one cavity. This cavity fixture serves as the foundational unit for assembling the complete mold. Once the individual cavity is ready, it is attached to the main mold fixture, forming the first part of the full assembly. Subsequently, additional cavities are assembled onto the main fixture to form a multi-cavity mold structure. Careful alignment ensures each cavity is precisely positioned. Once all cavities are in place, mold frames are assembled and mounted onto the main fixture to form the complete mold perimeter. These frames provide structural rigidity and dimensional consistency. For accurate welding and to ensure geometrical precision, the mold fixture is indexed. This indexing process aligns components in the correct orientation and fixes them in position for welding. Once alignment is confirmed, the welding process begins. Welders join the cavities and frame components together, creating a rigid and sealed mold structure. After welding is completed and cooled, the welded mold assembly undergoes disassembly. This step involves removing temporary supports, fixtures, and clamps used during welding and assembly. The mold is then prepared for inspection, surface finishing, and subsequent use in the production of B70 type concrete sleepers. Pre-stressed steel wires are inserted to add strength. High-strength concrete is mixed and poured into a mold, shaped like a railway sleeper. Next, workers level and compact the concrete in the mold. Then workers use a cutter to cut each piece of concrete out of the mold after it has hardened. The automated production of concrete railway sleepers involves a continuous. Modern plants, equipped with mold circulation systems like those developed by Vollert, make it possible to produce thousands of pre-stressed sleepers daily with minimal manual intervention. To begin with, the steel molds used to form the shape of the sleepers are cleaned thoroughly. As each mold returns to the starting point of the circulation system, it passes through an automated cleaning station, where rotating brushes and compressed air jets remove hardened concrete residue and debris. This step is essential for preserving the integrity of the molds and ensuring a smooth surface finish on the final product. Following the cleaning process, the molds proceed to the oiling station. Here, a thin, uniform layer of release agent is sprayed onto the inner surfaces of the molds. This non-stick coating is applied by robotic arms equipped with precision sprayers, ensuring even coverage and minimizing waste. The release agent prevents the concrete from adhering to the mold during demolding and helps protect the mold surface over repeated production cycles. Next, pre-stressing steel wires or strands are automatically drawn into the mold and placed according to the sleeper design. These high-tensile wires are then tensioned using hydraulic jacks under computer control. The tension applied to each wire is continuously monitored and adjusted to meet exact specifications. This pre-stressing technique enhances the load-bearing capacity of the sleeper by introducing internal compressive forces that counteract the tensile stresses from passing trains. Once the reinforcement is in place, attention shifts to concrete pouring. Concrete is prepared using automated mixing systems that accurately measure and blend cement, aggregates, water, and additives to achieve the desired consistency and strength. After mixing, the fresh concrete is delivered to the molds via an overhead shuttle system or concrete bucket. As the concrete is poured into each mold, an integrated vibration system compacts the material, eliminating air pockets and ensuring a dense, homogeneous fill. Sensors monitor the weight of the concrete to ensure each mold receives the correct volume. Depending on the production system in use, the concrete then undergoes either immediate or delayed curing. In immediate demolding setups, the molds are transferred into heated curing chambers, where controlled temperatures and humidity accelerate the hydration process. Within several hours, the sleepers reach sufficient early strength for removal. In contrast, delayed demolding allows the concrete to cure naturally at ambient temperatures over 24 to 48 hours, offering improved surface quality and mechanical performance. After curing, the molds move to the demolding station. Here, hydraulic actuators or mechanical levers open the molds, and robotic arms gently lift the sleepers out. At this stage, the pre-stressed wires are cut, transferring the stored tension into the hardened concrete and permanently locking in compressive stress along the sleeper's length. This process is crucial for the long-term structural stability of the product. Subsequently, the sleepers pass through finishing and quality control stations. Automated grinders or brushes may be used to smooth any rough surfaces. If required, machines drill holes or insert fastening elements according to customer specifications. Each sleeper is then subjected to rigorous quality checks. Dimensional accuracy is verified by laser scanners, while material strength and internal integrity can be assessed using ultrasonic or load testing methods. Any unit that fails inspection is removed for recycling or repair. After passing inspection, the sleepers are labeled with unique identification codes, batch numbers, and manufacturing dates using laser or inkjet printers. These markings ensure full traceability throughout the product's lifecycle. Finally, robotic stacking systems or gantry cranes move the completed sleepers into storage areas or load them directly onto transport vehicles. Meanwhile, the now empty molds are conveyed back to the initial cleaning station, and the cycle begins anew. Throughout the entire process, a centralized control system synchronizes the operation of all stations, monitors real-time performance, and ensures safety and efficiency across the production line. The process of making concrete sleepers begins with the preparation of the mold. The mold is thoroughly cleaned, and the steel shoulders are installed. Next, the steel wires are pulled through the mold and pre-tensioned to create the required compressive force. Shoulder locks are then installed to secure the wires in place. Workers move the machine and sit on the mold to evenly level the concrete, so that the high-strength concrete is poured into the mold, which is then vibrated to remove air pockets and ensure even filling. After casting, the mold is steam cured to accelerate the strength development of the concrete. Once the curing process is complete, the pre-poured concrete molds are cut. After the steel wires are cut, the sleepers are removed from the mold. Each sleeper is then quality tested to ensure it meets the required standards. These are pre-stressed concrete sleepers, designed to increase durability and load-bearing capacity. Finally, the finished sleepers are stacked and prepared for transportation and installation along the railway track. The forging process uses a hydraulic power head converted from steam. The converted hydraulic forging hammer lifts and drops the hammer head using hydraulic oil pressure. Nitrogen gas assists in returning the hammer. The operator controls striking force and speed precisely, achieving efficient and accurate metal forging. The process of changing a double-decker car wheel at the Wisconsin and Southern Railroad's Janesville rail yard begins by placing the car directly on hydraulic jacks on the tracks. These jacks are located underneath the racks, the load-bearing structure that connects the car body to the truck assembly. Crews ensure the car is stable and properly aligned on the jacks to ensure safe and efficient lifting. The repair starts with disconnecting the brake rigging. The crew removes brake rods, pins, and related hardware linking the brake system to the truck. They carefully loosen retaining bolts and fasteners, securing the truck to the car body, taking care to avoid damaging any components. This step demands precision to prevent stress on the brake system or truck structure. The crew inspects the center plate and side bearings for debris or damage that could hinder the process, ensuring all areas are clear before proceeding. With the brake rigging and hardware detached, the hydraulic jacks are engaged. Operating in unison, the jacks lift the car body evenly, raising it several inches above the truck to create clearance for removal. The crew monitors the lift closely, checking for instability or misalignment. This controlled elevation keeps the car balanced and protects the underframe from stress. The jacks hold the car securely suspended above the tracks, allowing the crew to prepare for truck removal. Once elevated, the crew manually removes the truck, which includes 2 axles, 4 wheels, side frames, bolster, journal boxes, and springs. Using pinch bars, they roll the truck out from beneath the car, leveraging the truck's wheels for smooth movement. Minimal force is applied to guide it clear, with care taken to avoid damaging the center plate, a pivotal connection point, or the guide surfaces ensuring alignment. The defective truck is then moved to a designated area for inspection or repair. A pre-inspected replacement truck with new or refurbished wheel sets is rolled into position under the elevated car. Using pinch bars, the crew maneuvers the truck along the tracks, aligning the center bowl with the car's center plate. This alignment is critical for weight distribution and stability. The crew makes fine adjustments, often manually or with tools, to ensure precise positioning. Visual and tactile checks confirm the center bowl and plate are perfectly aligned before lowering the car. With alignment verified, the hydraulic jacks are slowly lowered, transferring the car's weight onto the new truck. The crew monitors the descent to ensure the center plate engages correctly with the center bowl, and the side bearings make proper contact for stability. This gradual lowering prevents sudden shifts that could misalign or damage components. This is followed by a final comprehensive inspection. The crew verifies that the truck is properly positioned, the center plate and center bowl are properly installed, and the side bearings are operating as intended. They check the brakes for proper clearance and alignment, ensuring that the brake pads are not stuck to the wheels. The hydraulic jacks are removed from the tracks, and the car undergoes a brief operational test to confirm that the car rolls smoothly and is safe to use. The entire process is performed with precision and in compliance with safety protocols, ensuring that the car is fully restored to service with minimal downtime. A thorough final inspection ensures the truck is properly seated, the center plate and center bowl are engaged, and the side bearings function correctly. The crew checks brake clearance to prevent binding against the wheels, confirming operational safety. The hydraulic jacks are removed, and the car undergoes a brief test to verify smooth rolling and service readiness. The reprofiling process of train wheels using the underfloor wheel lathe UGE 150N begins by positioning the rail vehicle above the machine, which is installed in a pit-tight foundation. Without dismantling the wheel sets, the wheels are aligned and clamped either by rotary centers or holding down pads. Each wheel is then driven by two rollers with individual drive units and flexible pressure mechanisms. Once secured, automatic measuring devices scan the wheel profiles. Based on this data, the CNC system adjusts the machining parameters. The crossrail, mounted on two rigid cast iron columns, ensures high stability during cutting. Each saddle carries a cutting tool that reprofiles the wheels with precision. Throughout the process, the operator monitors and controls machining via a user-friendly CNC control panel, displaying step-by-step instructions and system diagnostics. Optional equipment allows simultaneous reconditioning of brake disc surfaces. Upon completion, the wheels are released and the vehicle can be moved away. This efficient process significantly reduces downtime while ensuring optimal wheel geometry and braking performance. The 4.5 kilometers Gong tunnel, Kenya's longest, is being constructed for the Phase 2A. Excavation progresses at 2.5 meters per day. Designed for a single track, it measures 7.6 meters high and 6.4 meters wide. The tunnel enables trains to pass through cliffs efficiently, supporting project completion by mid-2019. Railway flash butt welding involves aligning and clamping two rail ends between copper electrodes. An electric current is passed through the joint, causing resistance heating, and creating sparks that expel impurities and oxides during the flashing phase. Once the desired temperature is reached, the forging phase begins, where the rail ends are pressed together under high force to consolidate the molten metal and form a strong bond. The weld is then trimmed and allowed to cool. Strict quality checks are conducted to ensure weld integrity and performance. Concrete sleepers undergo certification tests, including repeated and vertical load tests on rail seats A and B, positive and negative bending moment tests, resistance and impedance measurement, and a longitudinal restraint test to ensure structural strength and performance. The hydraulic forming process for the dish end begins with cleaning and lubricating the metal plate to reduce friction. The plate is then heated to increase its malleability. After heating, the plate is placed into a die, where high-pressure hydraulic fluid pushes it into the desired hemispherical. Once formed, the dish end is cooled to room temperature before removal. Finally, excess material is trimmed and the edges are flanged to meet specifications. This process produces precise, strong dish ends used in pressure vessels and other applications. The tamping process begins by spreading crushed stone evenly along the railway track bed. Specialized machines distribute the ballast to fill the gaps beneath and around the sleepers. Once the crushed stone is positioned, tamping machines engage to compress and compact the ballast under the sleepers. These machines use vibrating tines that penetrate the ballast and shake it into a denser arrangement, effectively stabilizing the track structure. This compaction ensures proper load distribution and prevents track deformation during train operations. The tamping process is carefully controlled to maintain the correct track geometry and alignment. By firmly securing the sleepers, this step significantly enhances the durability and safety of the railway line. The mechanized track laying process at Bedon involves preparing the track bed, positioning sleepers precisely, laying rails using specialized machines, aligning and leveling the track, and fastening rails securely. This ensures fast, accurate construction with improved track stability and safety. The CQS 550 ballast cleaning machine performs full section screening for both turnout and mainline ballast beds. During operation, it excavates ballast without disassembling the bottom beam or digging chain, significantly reducing setup time and labor. Excavated ballast is screened, and clean material is redistributed evenly via left-right conveyors, center funnel, regulated by a ballast distribution system. Contaminated soil is expelled through a rotating discharge belt to either side and loaded into transport wagons. After complete ballast removal in turnout zones, new ballast is refilled promptly. The machine operates under video monitoring, displaying real-time conditions and machinery status to ensure safe, efficient cleaning. The FRM 85 ballast cleaning machine lifts the track, removes dirty ballast, separates it from debris, and returns clean ballast. Additional fresh ballast is added if needed, and the track is relayed and leveled, ensuring proper drainage and stability. The construction of the 350 km/h high-speed railway involves the use of the SLJ 930, a massive bridge girder erection machine. Also known as the Iron Monster, this 91-meter-long, 580-ton machine streamlines the installation of precast concrete bridge segments without the need for large cranes' extensive ground clearance. The process begins at a beam storage site where the SLJ 930 seconds drives sideways using its 64-wheel drive system split into 4 steerable sections. This lateral movement allows it to position itself precisely over a precast girder section. The girder is then hoisted beneath its central body. Once loaded, the vehicle travels along the previously constructed portion of the bridge at up to 5 kilometers per hour, carrying the massive beam toward the installation site. Upon arrival, it anchors to the first bridge pier using a pneumatic locking system. The front end of the machine then extends over to the next pier. With the vehicle secured on both piers, the concrete beam is aligned and carefully lowered into place. After installation, the machine detaches and moves forward, repeating the process for the next span. This method allows continuous installation without dismantling or repositioning auxiliary cranes. The SLJ 930 seconds can build up to 730 bridge spans in its lifetime. Its unique ability to operate in narrow construction corridors and bypass obstacles makes it a vital tool in high-speed railway construction, ensuring both speed and precision in erecting long viaduct sections efficiently. The track renewal process at kilometer 7.4 begins with the precise alignment and integration of the track renewal train into the existing railway infrastructure. During this initial stage, the train gradually merges onto the track section to be renewed. Once the train is properly aligned, the main renewal operations commence. The first step involves the removal of the old rails and sleepers. Hydraulic clamps and cutting tools mounted on the train release and separate the rails from the sleepers. The rails are carefully lifted and pushed aside by powerful mechanical arms. Simultaneously, an integrated conveyor system extracts the old concrete sleepers. These sleepers are removed from the track bed and transported via chain conveyors onto transport wagons for disposal or recycling. Following the removal of the old track components, attention shifts to preparing the ballast bed. The ballast, which provides structural support and drainage beneath the sleepers, is inspected for compaction and cleanliness. Fresh ballast is spread evenly across the track bed by conveyor belts connected to the renewal train. Specialized vibrating and tamping units compact the ballast to create a stable foundation that will support the new track components. Next, the installation of new sleepers begins. Using automatic sleeper feeders, new concrete sleepers are precisely placed in correct intervals on the prepared ballast bed. The positioning is carefully controlled by laser and GPS-guided systems to ensure exact spacing and alignment in accordance with the railway standards. After the sleepers are in place, the next step is to lay the new rails. Long welded rails are delivered on transport wagons and fed into the track renewal train. Hydraulic manipulators guide the rails onto the sleepers, aligning them with high precision. Once positioned, the rails are fastened securely using modern clip fasteners. Throughout the entire process, tamping machines operate continuously to compact ballast beneath the sleepers and correct track geometry, both vertically and horizontally. Laser-guided measuring devices constantly monitor the track gauge, elevation, and alignment, enabling real-time adjustments for optimal track quality. Workers on board and alongside the renewal train oversee the operation at every stage, performing manual adjustments and ensuring compliance with safety regulations. After the installation is complete, a trailing inspection unit follows the train to perform thorough quality control. It checks parameters such as track geometry, sleeper spacing, rail alignment, and ballast distribution to confirm that the renewed track meets all technical and safety standards. By the end of the renewal operation at kilometer 7.4, the entire track section has been transformed with new rails, sleepers, and a properly compacted ballast bed. The construction of the S3 railway line in Langenzersdorf, Line Austria, is a highly organized process that includes several key stages to ensure long-term performance, safety, and structural stability. The project begins with the preparation of the roadbed. Excavators remove the old gravel and soil to create a solid foundation. The roadbed is leveled and compacted using vibratory rollers to prevent settlement and create a solid base. Next, a new layer of gravel is laid using specialized machinery. The gravel serves multiple purposes. It distributes the load from passing trains, provides drainage, and maintains track alignment. The old, damaged sleepers are then removed, and new precast concrete sleepers are placed at precise spacing. These sleepers are positioned using mechanical arms or sleeper laying machines, ensuring the correct gauge and spacing across the entire track. After the sleepers are installed, long welded rails are delivered and placed on top of them. A rail threading machine or crane handles these heavy steel rails. Workers manually fine-tune the rail position to meet exact joint specifications. Temporarily clamp and pin the rails before final joining. The rail joining process is performed using the Thermite welding method. The rail ends are carefully aligned and cleaned. A ceramic mold is placed around the joint and preheated. A melting pot containing a mixture of powdered thermite and iron oxide is then ignited. The exothermic reaction creates molten steel, which flows into the mold and melts the rail ends. Once solidified, the mold is removed and the excess metal is ground to create a flat, smooth surface. Once the rails are fully joined, the track profile is finalized. A track compactor lifts and vibrates the track while packing the gravel beneath the sleepers to eliminate voids and ensure proper flatness and alignment. Laser systems and measuring instruments verify the accuracy of the track profile. Finally, all fasteners are tightened and the area is cleaned. Quality control checks, including ultrasonic testing of welds and visual inspections, are performed before the track is approved for operation. The result is a high-quality track ready to support reliable train service on the S3 line.